Okay. Good morning. So you are perhaps 20 of you joined, and in our previous class we have finished stability, transient stability analysis. This was done. Some problems solved, and today I shall be starting with excitation system. So basically, we have finished at the beginning. We have discussed basic issues related to the uh, uh, voltage and frequency control of power system. Then we have discussed regarding the representation of generator, because the control of voltage and frequency, in my part, I have to discuss what is possible from the generator end, from the power plant. So that side I am doing, I am covering. So I have discussed about the synchronous generator and also partly for synchronous motor, because synchronous motors are also used for voltage control. Then we have discussed the load frequency control. That means how the frequency will be controlled in a system when load is varied. This part was discussed. Theory portion I have discussed. Some problems are to be solved. Some problems are to be discussed. I shall be discussing these problems in my next class. Okay. Then I have started stability. I have discussed basic issues of stability in power system, particularly voltage stability and angle stability, and discussed in details means uh, that much that is possible for an undergraduate course. Okay, the undergraduate general course, of course. So I have discussed the basic issues of angle stability and steady state stability, dynamic stability. This I have mentioned, and then finally I have discussed transient stability, how tangent stability problem can be analyzed with the help of equilibrium criterion, because equilibrium criterion basically helps you in understanding the stability, and that is the best way of understanding the basic problem of stability, particularly tangent stability in power system. Okay, I have solved some or discussed some problems also on transient stability, and also discussed the methods for improving the stability in general and transient stability in particular. Okay, so all these are done. Maybe you are having some questions. All these questions I shall be actually attending in my next class. Today I shall be discussing the excitation. That is, for voltage control for synchronous machine, you have excitation system. For frequency control, you have the governors. Governor model we have discussed, and how it functions also we have discussed. Now let us discuss the excitation system, how it functions. What are the variations available? Okay, because for voltage control and reactive power control, you have to depend upon the excitation system. So what is the excitation system? It is the system that actually supplies field current to the synchronous generator. That excitation system we shall be discussing. So field current is DC current. So what are the basic functions of excitation system? It is in my PPT. Perhaps you can see. So we shall be discussing these points as written here. Point wise I shall discuss. It supplies DC current to the field winding. So the basic function. Who will be supplying field current? A DC generator is required sometimes. Sometimes a separate generator is used. Sometimes a separate DC generator. Sometimes a separate AC generator. Sometimes the same generator whose excitation we shall be controlling will be used to supply field current to the same generator. That means the generator will be self-excited. Okay, these issues we shall be discussing, but the basic function is to supply DC current to the field winding and automatically adjust the field current to maintain the terminal voltage. The output changes. This I have mentioned that for voltage control, who takes the primary or lead role in the voltage control of power system? It is the synchronous generator itself. And for controlling the voltage as the load varies, universally it is the practice that the terminal voltage of the generator will be kept constant. This is done. So terminal voltage will be kept constant so long it may be kept constant. Sometimes, depending upon the loading condition, it may happen that you cannot keep the terminal voltage constant. In heavy loading condition or very when the load is very poor, very low, then it may so happen that you cannot make the field current constant. It exceeds the capacity of the excitation system. Then it will not be kept constant. It will not be possible to keep it constant. So if it is possible to keep the field current constant, then the exciter will do it. And this is the function of the excitation system, to maintain the terminal voltage and output changes. Output changes throughout the day. So every second it is changing. So every second exciter will be adjusting its field current. Okay, field current will be adjusted by the excitation system. Again, we have mentioned while discussing the dynamic stability, and this again is a problem that exciter is maintaining the terminal voltage constant. That means it is always changing the field current. That means always there is some control disturbance applied to the generator field. You are applying control, but that again is a disturbance somehow. And that disturbance may initiate the problem of dynamic stability. And for controlling the dynamic stability, again you have to depend upon the field current. And again, the field current variation has to be adjusted. It has to be done in a different way such that the dynamic stability may be actually controlled, may be maintained in the power system. So it is a function of the excitation system to maintain the constant terminal voltage by constantly adjusting the field current. What is the other functions? Control system voltage and reactive power flow. So what is that? It does not only maintain the terminal voltage constant whenever it is adjusting its field current, it is delivering reactive power also or absorbing reactive power also. So by doing this, it is maintaining its terminal voltage constant and at the same time either delivering reactive power or absorbing reactive power, and it helps in maintaining the total system voltage within a defined or in a prescribed limit. Okay, so not only the terminal voltage is being kept constant, according the excitation system will be controlling the system voltage as a whole in that way, and also it will be controlling the flow of reactive power, because only way of maintaining the terminal voltage constant is to adjust the field current by the generator, and the generator is adjusting its field current, it is also adjusting its reactive power output. As the reactive power output of the generator is being adjusted, the reactive power flow in the system also will be adjusted. It will again be monitored. Okay. So therefore, this again you can say is a function of the excitation system. Okay. Now it enhances transient stability. While discussing the methods for improving the transient stability, I have mentioned this. If you want to control the transient stability, a good method is also to control the excitation voltage, control the field current, because as you are controlling the field current, what is happening? Generated voltage is changing. So depending upon the requirement, you may increase the generated voltage, you may decrease the power generated voltage. That means you may increase the peak of the power angle curve and you may decrease the peak of the power angle curve. That means power angle curve, when the field current is adjusted, field current is changed, it is no longer a single power angle curve. Power angle curve will be changing. Okay. Whenever the field current is changed, there will be different power angle curve. So in this way, you can have a control over the available accelerating power or available decelerating power. So depending upon the requirement, you may either increase the accelerating power when the generator speed is reduced, or you may increase the decelerating power when the generator speed is increased. So this has to be again changed dynamically. That means whenever you are changing the field current, this has to be changed dynamically upon the requirement. If it is needed to absorb power, okay, sometimes it may be needed to increase the accelerating power, or sometimes it may be needed to decrease the accelerating power. Okay, so this is done by controlling the field current. That means transient stability enhancement is possible, and it is practiced also by changing the field current. And also it enhances dynamic stability. Already I mentioned that the the cause for the dynamic stability problem in power system is the excitation system itself. And at the same time, this excitation system is again adjusted, it is again used to control the or to enhance the dynamic stability. So obviously the control effort will be taken depending upon some decision making process. Okay, that helps in adjusting, that helps in improving the dynamic stability. Okay, and this for that the so-called power system stabilizer is introduced, and this is there along with the we shall see that in the components of excitation system there is one that power system stabilizer. That stabilizer basically adjusts the field current of the generator, and by doing this, it enhances the dynamic stability. So these are the functions of the excitation system. And what are the requirement? Requirement are should be capable of responding rapidly to disturbance. That means it has to be faster. Acceleration system of old days were not that fast because those were actually basically DC generator were used and they are sluggish. So people has actually shifted from DC generator to AC generator, and all these control nowadays are actually implemented through power electronic controller, which are very fast. So speed response is very important because you have to control the field current very fast. So it is also a requirement that this response time should be very low. Okay. So high ceiling voltage. High ceiling voltage means how much you can increase the excitation voltage, how much you can increase the field current. Obviously, if the exciter has a very large, you can see that voltage capacity, that means if the ceiling voltage, maximum voltage is very high, then obviously exciter may increase its voltage to deliver more and more current, because exciter will be delivering current to the field winding of the generator. Okay, so it has to overcome the impedance of the field winding, and available voltage divided by that impedance will determine the current. So with the ceiling voltage, that means maximum voltage available that the exciter can reach, if that is available, you can control through a wider range. So that high ceiling voltage is again a requirement from the exciter, that it will be capable of changing the field current or increasing the field current to very high value. And obviously it is depending upon the, it will be limited by the capacity of the rotor winding or the field winding. But if the capacity is, then the exciter must be able to increase the field current, and if the field current has to be increased, then available voltage of the exciter, that means the generator that is delivering power or delivering the DC current, has to be very high. That is the meaning of this ceiling voltage. And capacity that is required to do this is 2 to 3.5 kilowatt per MVA. That means per MVA capacity of the generator, what will be the capacity of the exciter? How much is the capacity of the exciter required to drive current to a synchronous generator? This is 2 to 3.5 kilowatt per MVA. Okay, so these are the requirements and these are the functions. Then components. What are the basic components of excitation system? Yes, so these are shown here. So as if this is the generator, our synchronous generator. It is shown by means of blocks only. Okay, this is the generator. The terminal voltage. It will be terminal voltage will be measured. Okay, who will be measuring this terminal voltage? The terminal voltage transducer and load compensator. So function of this terminal voltage transducer is basically the current transformer and potential transformer. Current will be measured by obviously it will be the measurement system will take the help of current transformer, because current has to be reduced. Okay, whenever it is measured, it is to be reduced. So similarly, generated voltage has to be reduced, so it is done by the potential transformer. So there are CTs and PTs. So this is written here as the current, terminal voltage transducer and load compensator. What is load compensator? That I will discuss. This load compensator actually helps you in compensating the effect of the load. How it does, I shall discuss later on. Okay, after this slide, I shall be discussing this. So this is terminal voltage is being measured through this transducer, current is measured, and load compensator is used to adjust or to compensate for the drop in the terminal voltage because of the presence of some impedances. Okay, and how it does, I shall explain. Then this is the exciter. Exciter means the generator, the physical generator that is actually supplying the field current to the generator. So exciter basically is a generator, and this exciter may be a DC generator, maybe an AC generator, or maybe the same generator. That means this generator whose field current we shall be adjusting, which field current we shall be controlling. The same generator may be used to drive field current to the generator. So then in that case will be self-excited. So in that case, basically, the terminal voltage will be stepped down separately. It will be stepped down for the purpose of excitation system, and then it will be rectified and then used as an exciter. Okay. And regulator means that controller that controls the field winding of the field current of this exciter. That means exciter field current again has to be controlled so that it generates the desired voltage, and that desired voltage will be used to change the field current of the generator. Okay. Therefore, exciter again has to be controlled. How it is controlled? With the help of regulator. So this regulator decides how much will be the change in the field current of the exciter and how much the field current of the main generator has to be adjusted. All these things is regulated, actually adjusted or decided by the regulator. Where from it is taking the input? It is taking the input from terminal voltage transducer and load compensator. So that the voltage is reduced, current is reduced, and desired voltage and current is decided by the load compensator and then given as input to the regulator. Regulator as a reference. What is this reference? How much should be at what value the voltage has to be kept constant. Okay. That means generally the terminal voltage will be kept constant. The value of that will be taken as reference. Sometimes this reference also has to be changed. So I shall discuss when this reference has to be changed. Okay. So this reference is also given as input because such that this reference may be compared with the available voltage. Okay. Then limiter and protective circuit. Actually, so the function of this limiter and protective circuit is to uh, limit the field current. Okay, limit the field current and limit the excitation system against any damage. Okay, there we know that there is a maximum field current limit, there is a minimum field current limit. All these are adjusted, all these are actually verified by this limiter and protective circuit. Okay, how much field current we can increase? Sometimes that is to be determined by some other thing. What are the some other thing? You see there, it basically it controls the overexcited. There is overexcitation limiter. That means you can increase the field current. Normal field current. What field current is the normal field current? That gives you the unity power factor condition that we have mentioned while discussing the generator. That there may be normal excitation. That normal excitation corresponds to the operating condition when the power factor of the generator is unity. Okay. If the field current is above this, generator will be delivering more reactive power, operation will be lagging, and it is overexcited. When the field current is reduced from the normal excitation, then generator will be operating as a leading power factor. So generator will be observing reactive power. So basically, this limiter and protective circuits, this component, we have here we have the over excitation limiter and under excitation limiter. Under excitation, limit of under excitation, already we have mentioned, and if you remember, it is decided by the stability, steady state stability of the generator. Okay, and over excitation limit, it is decided by the heating of the field winding. So these limits are to be monitored by somebody, and that is done by the protective and limiter circuits. Terminal voltage limiter. Okay, that means sometimes when the generator cannot maintain the terminal voltage, so what is done? Then the capacity of the exciter is exhausted. Then you have to limit. You cannot allow the generator to increase the volt current, terminal voltage to such value that it may be dangerous for the system. And that is actually checked by the terminal voltage limiter. Okay, voltage generally will be kept constant if it is within the capacitor. But sometimes the capacitor exciter capacity may be exhausted, and then it will not be in a position to maintain the constant terminal voltage. Then the generator is operating say at a higher generated voltage. So that has to be again checked. And who does this? It is the terminal voltage. And volt per hours regulator. Volt per hours. What is volt per hours? If I divide the generated voltage by frequency, what you will be getting? Anybody? Can you tell me if the generated voltage is divided by the generated frequency, what is the value? What we get from voltage per hertz, that is volt by hertz. What is the parameter here? What is volt by part? Volts by hertz? Sorry, hertz. Anybody? Generated voltage.
Frequency regulation.
It is?
Frequency regulation.
No. Think of it. Generated voltage is being divided by frequency. What you will be getting? What is the parameter you will be getting? For a generator, how the voltage is generated? It has to rotate in a magnetic field. Okay, while with the magnitude of voltage will be decided by the speed of rotation and the magnitude of the flux. Okay, then armature is rotated in a magnetic field. So what decides the generated voltage? Basically, it is decided by the speed of rotation of the generator and the flux. So volts per hertz. When we are dividing generated voltage by hertz means frequency, then obviously we shall be getting the flux. So these will give you volts per hertz. It will give you the measure of flux. Okay, inside the generator. That means it will decide, or it will decide, basically determine what is the flux generated inside the core of the generator. Okay, so indirectly it is being measured. Generated voltage divided by hertz, and how much should be the flux density? There should be a limit, and that limit is being checked by this volts per hertz regulator. Okay, so basically the over excitation is monitored, under excitation that is monitored, terminal voltage is monitored, there is a limit above which you should not go. Okay, then volt per hertz regulator, that means over whether there is overfluxing or not. If there is overfluxing, that means if there is saturated, then some unwanted situations will take place. That has to be avoided. So protective limiter and protective circuit, obviously it is a very useful thing, it's a very necessary thing. Okay, useful thing for this excitation system, and these are the important functions done by these limiters and protective circuit. Okay, so and finally the power system stabilizers, as I mentioned, it provides additional input to the damper to damp system oscillation. Basically, what happens during the dynamic condition when the field current is changed? When the field current is changed, there is an additional torque introduced into the system. A variation in torque is introduced into the system because always the field current is changed means flux is changed means there will be variation in the generated torque. Okay, so that will create a variation in the speed of rotation of the generator, and that variation, if it coincides with the natural frequency of oscillation of the rotating mass, then this creates the major problem that if resonance will be created, and because of this resonance, the small oscillation because of the variation in field current will be actually becoming bigger and bigger, and this will lead to the collapse of the system. This will be lead to the loss of the dynamic stability of the system, and this is being checked by power system stabilizer. How it takes the power system stabilizer checks it. Commonly used inputs are rotor speed deviation. How much is the speed deviation? Accelerating power or frequency deviation. So basically by seeing or by measuring the speed deviation, okay, or accelerating power, how much is the accelerating power? Okay, difference between input and output is the accelerating power, and how much is the frequency variation. So basically speed variation or frequency variation, they are same thing. Some system will be using the speed variation, some other may be using the frequency variation, frequency deviation. Okay, so these two are identical thing, means the form of measurement is that different. Okay, so either accelerating power or speed or frequency deviation, these are being measured, and accordingly as required the field current is adjusted, so it will give signal The output of this power system stabilizer goes to the regulator. Regulator, by taking the inputs from various components, decides how much will be the field current of the generator. At what value the field current of the generator has to be adjusted. So these are the different components of the excitation system. Okay. Now come to this figure. This particularly here, this is showing the load compensator. I have mentioned the load compensator here. You see that terminal voltage transducer and load compensator. There is one component. I have mentioned that the function of this component is to compensate for the load. How it compensates for the load? Say, I shall be maintaining the terminal voltage of the generator. Okay, I shall be maintaining for the terminal voltage of the generator. Then the current delivered by the generator is measured by the current transformer. Why it is measured by the current transformer? I should discuss. And terminal voltage is measured by the potential transformer. So sometimes it may happen that not the terminal voltage, but a voltage beyond this transformer has to be kept constant. Requirement may vary. Okay, for control phase, actually implementing the control, it may so happen that you want to maintain this voltage constant, not this voltage. So whenever, what is the difference? If you maintain this voltage constant, then what will happen? Then there will be some voltage drop in this transformer. If the load increases, obviously more voltage will be dropped here. So here the voltage then available will be less. Or sometimes you may be interested in controlling a voltage which is inside the generator. That means, why inside the generator? Because generator, there is generated voltage. Then if you remember the phasor diagram or equivalent circuit of the generator, we have shown the generated voltage and then the synchronous reactance at steady state or transient reactance during the transient condition. So there is some impedance of the generator. We may wonder a voltage not just at the terminal of the generator, but inside the voltage, so inside the winding, the voltage that is there inside the winding will be controlled. So how we can do this? So it can be done by simulating a drop here. Okay, simulating a drop here. If you want to control this voltage, then these RC and XC, that means the control resistance and reactance, these will represent the impedance of the transformer. Okay, if you want to control the voltage inside the generator, then these RC and XC, they will actually represent the impedance of the generator before which we want to control the voltage. We want to keep the voltage controlled at the value which is available inside the generator. So obviously inside the generator there is generated voltage and some impedance, and we want to control that voltage constant inside the generator. So some impedance that is representing of the winding impedance here, or part of the winding impedance will be represented by RC and XC. Accordingly, value will be adjusted. Okay? And then what we shall be doing? This is the measured voltage. If you want to control this voltage, then you will be measuring this drop because current is flowing here. Replica of this impedance is available here. So this voltage minus this drop will be the voltage here. That this voltage is basically it is calculated in that way. Okay, we are not taking direct measurement here. Here this voltage is being measured and this voltage is calculated and that voltage is controlled. Or if you want to control a voltage inside the generator, then drop inside this winding, representation of winding of the generator is here, and this voltage plus this voltage, then a voltage which is higher than the terminal voltage has to be controlled. Though we shall be calculating that voltage with the help of load compensator. So load compensator basically is this part. So it is basically compensating for the drop due to the load current. What we are doing? We are either subtracting this voltage drop or adding this voltage drop. And how much is the voltage drop here? That voltage drop depends upon the present value of the load. How much current is being delivered by the generator. That's why it is called the load compensator. So it compensates for the drop in the external transformer because of the flow of load current, or it compensates for the, or it adds the voltage which is the representation of the drop in the part of the winding which is inside the generator. Okay, in that way we should be controlling a voltage inside the generator, or we should be controlling the voltage which is outside the generator. So load compensator helps us in calculating that voltage. Okay, so that is remaining thing is all right. So same, this voltage regulator means that regulator we have mentioned here. This regulator, okay, this regulator is there. So input is given to this rate compensator. From this load compensator, it comes here. That is shown here. Okay, that is shown here, and then it goes to the exciter right there. And exciter has the field. The field current is controlled, and accordingly the generated voltage will be controlled. Okay, so this is the function of the field excitation system, and this is representing the function of the load compensator. Okay, obviously the purpose of this transformer is so generated voltage is not very high. Why? Because inside the generator you cannot generate a very high voltage because of the limitation of the size of the generator. How much insulation you can provide inside. So generated voltage is less. It has to be stepped up, and then it is the transmission voltage of the HT bus. From where the high tension bus, that means high voltage bus, from here the transmission line will actually go outside the power station. Okay. Now, what are the types of excitation system? Now, the types of excitation system basically is decided by the type of the exciter. Means it may be a DC exciter, the DC generator may be used, and the name will be DC excitation system. It may be a maybe an AC generator. Exciter itself basically maybe an AC generator. Then the name is AC excitation system, or it may be static excitation system, because in that case the generator will be self-excited. And why it is called static? Because the generated voltage is rectified in the rectifier. That's why it is static. Means static means on a sometimes electronic circuit we call this static devices. Okay, that's why it is called the static excitation system. So DC excitation system, DC generator is the power source. Main function of the exciter is to deliver power, deliver field current. DC generator output is fed to the field winding through slip ring. This is one disadvantage of DC generator, because there it has to be supplied to the field winding on the generator through slip ring. Because why is through slip ring? Because you know that the in synchronous generator field winding is rotating and armature is stationary. Because why the field winding is rotating? Because field winding has a lower power rating. So obviously the involved current will be lower. So it is easier to handle this lower current slip rings. That's why the field winding is rotating here. So generated voltage through slip ring will be delivering current to the field winding of the generator. So generator itself may be self-excited or separately excited, because you know about DC generator. DC generator may be self-excited, so self-excited generator may be used, or separately excited generator also may be used. And these DC generators were used in old machines. So nowadays, hardly this type of excitation system will be available, because in newer machines, okay, after 60s, all generators now they use AC generator or static excitation system. In older generators, the DC generator or DC excitation system were used. Okay, why they have been replaced? Because of the problem involved in the DC generator. What is this problem? Long time constant. Okay, because how can you control the field current generated by the DC generator? You have to control the generated voltage of DC generator. So for controlling the generated voltage, you have to control the either the speed of the generator or the field current of the generator, and that again is very time consuming because it has some inertia. If you are changing the speed of the generator, then it takes some time. that time is not very small. And for controlling the field current, you see that the time requirement or time that may be allowed is very, very small. So we have to be as fast as possible. That's why people have shifted from DC generator to other devices. Okay. There is another problem, that is the commutation. And this is a very well-known problem of DC generator. Why? DC generators are good, DC machines particularly, DC motor, DC generator, they are obviously having very good characteristics, but their problem is that here the commutation is a problem, big problem. There will be sparking. Okay, so because of this commutation and long time content involved in DC acceleration system, they are no longer in use except for very old generator. Okay, so basic problem is that here response is long. That response time will not fit today's generator, where you have to control a very, very complex system, because power system is a very complex system involving hundreds of generators, hundreds of rotating loads. Okay, so system is very complex. You have to act very fast, and for acting very fast, you cannot depend on DC acceleration system, because you cannot depend upon the DC generator. And DC generator again has its own inherent problem, that is the problem of commutation, sparking related to the commutation. Okay, so AC excitation systems are used, or static excitation systems. What is AC excitation system? Here, a separate alternator is used as the power source. So you have a separate alternator, separate generator, and that again is an AC generator. Okay, AC output is rectified in controlled or uncontrolled rectifier. So obviously, since you are having an AC um, machines, AC generator as the exciter, you will be finally delivering direct current. So obviously, you have to rectify the output, rectify the current delivered by the, okay, because this is AC generator. This is not the case in case of DC generator. In case of DC generator, it is delivering direct current. We does not need any separate rectifier. But in AC system, you need some rectifier, because it has to be rectified, because unidirectional current is required. AC output is rectified in controlled and uncontrolled rectifier. Then rectifier may be of two types, maybe controlled rectifier, maybe uncontrolled rectifier. Controlled rectifier means they are using thyristor, okay, and uncontrolled rectifier means they are using the diodes. Okay, sometimes it may not be possible to control the rectifier, then we go for uncontrolled rectifier. But whenever the control is possible, then people go for control rectifier. The situation is such that you cannot apply the control on the rectifier. So people go for uncontrolled rectifier. We shall show when this is the case. Okay, which are either stationary or rotating. So again, these rectifiers, they may be stationary or they may be rotating. That means rectifier may be placed on some rotating system. Rectifier may be placed on some stationary system. When the rectifier is placed in rotating system, the rectifier system is rotating. When they are placed on stationary system, it is the stationary rectifier. And static excitation system having no additional rotating part. This is very advantageous here, because you can avoid an additional rotating part. Whenever you can avoid an additional rotating part, you can immediately improve upon the reliability of the system, because lesser the components, more reliable in the system. If the number of components in the system increases, whatever may be the system, when more number of are there, obviously the system has to be less reliable, because problem may occur in any of these devices, any of these components. So if you are if you can restrict to a small number of components, you can have a better reliability. So having no additional rotating part, this is an advantage. Generator output is stepped down. Already I have mentioned that generator output, the generated voltage will be stepped down. Maybe using a separate winding will be there for this type of generator, or you may be using separate transformer. Okay, separate winding of the transformer, where you will be actually stepping down the voltage and rectifying it. Okay, rectified and fed to the field winding. Why I am talking about a separate transformer or separate winding? Because generally generator output voltage will be stepped down, because for transmitting power, always you have to go for higher voltage. If the higher voltage is high, then only you can transmit large power. So generator, if a generator is large capacity, modern days generators are of very large capacity, conventional generators. Either it is hydroelectric or steam thermal power station. Generators are of large capacity, and since the generators are of large capacity, you have to go for higher voltage, because at low voltage you cannot transmit large power. So you will be using step up transformer. But when the excitation system is static, then you have to use a separate transformer winding or separate winding of the generator, whatever is there, to reduce the generated voltage. Okay, because generated voltage has to be reduced, stepped down, and then rectified and fed to the field winding, because field winding is of lesser voltage, smaller voltage. Generated voltage is higher compared to the exciter voltage. That's why it has to be reduced. Okay, so these are the types of the excitation system. Now, let us discuss about these various types. First of all, the stationary rectifier system. I have mentioned that from AC generator, the output voltage has to be rectified. It has to be rectified using controlled or uncontrolled rectifier system. And this controlled or uncontrolled rectifier system may either be rotating or maybe stationary. Okay. So first of all, consider the stationary rectifier system. The field controlled alternator rectifier excitation system. So field controlled alternator rectifier excitation system. We shall see how can we justify the name of this excitation system. Let us first see the operation of this of this excitation system. Here, this is the main generator armature, and this is the field winding of the main generator. You have CTs and PTs. Obviously, this will go to the regulator. Input will go to the regulator. That part we have discussed. Now there are two regulator. One is DC regulator, another is AC regulator. Okay, AC regulator is using actually output of the output voltage and current of the generator, because output voltage and current they are AC. Okay, there is some auxiliary inputs. What are these auxiliary inputs? That other devices, then the stabilizer, protective circuit, and all this. From all those components, input will be there. So auxiliary inputs, as we have seen previously. And this is the AC reference. AC reference means how much, which voltage has to be controlled. What is the value of that voltage? That will act as the AC reference. Okay. And you see that this DC regulator and AC regulator, they are in parallel. That means when one is used, this will, when it is closed, it will be open. When this is closed, this will be open. That's why they are in parallel. So there is one DC regulator. It has a DC reference. What is this difference? This reference is how much will be the voltage, DC voltage, that we shall be maintaining here. Okay, how much will be the voltage here, DC voltage of the exciter. Okay, that will be controlled. This is the DC regulator. And where from the AC, other input is coming? It is coming generator. How much is the generated voltage? This is coming from here. Okay, from the terminal of this exciter output. Okay, so AC generator, exciter is an AC generator. It has separate field winding. It has the armature winding. Armature winding voltage is rectified through uncontrolled rectifier. It is uncontrolled rectifier. So again, so it will be DC voltage available here. Dash DC voltage is measured by the DC regulator, and it is compared with the reference voltage. And accordingly, the field current of this alternator is controlled. Who controls this? This controlled rectifier controls this. So for this, what is done? Output voltage of this exciter is controlled here through controlled rectifier. Okay, and field current is changed. Then who actually controls the control of this rectifier, control rectifier? That is the DC regulator or AC regulator. So DC regulator actually will operate when the AC regulator is not available. When the AC regulator is not available, then only the DC regulator will be used. And when the AC regulator will be used, then obviously this will be turned off. Okay, so regulator controls the field of the self-excited exciter. The exciter is self-excited. Means initially you will not get any voltage because it is the exciter. It has to build up its own voltage. Okay, and how much it will build up, how long it will build up its voltage, that is then initially therefore the DC regulator will be operating. Okay, initially the voltage has to reach the required voltage, required DC value. Okay, that is therefore being regulated by the DC regulator. So during initial period, the DC regulator is effective, and then AC regulator will come into operation. Okay, after AC regulator takes up the job, then DC regulator will be made off. Okay, so what is the purpose of this regulator here? They controls the field current of the generator by measuring either this voltage or by measuring the voltage here. Okay, that means the control of output voltage is controlled, is control of output voltage is done by the regulator, which is either DC regulator or AC, by controlling the field current of the exciter, by controlling the field current of the exciter. Because why by controlling the field current of the exciter? Because you are not controlling it. So you are controlling the field current, accordingly controlling this voltage, and again that voltage is rectified. It is uncontrolled rectifier, means whatever voltage is available, that will be controlling the field current. So you cannot have, you are not having a separate control of the field winding current of the main generator. Rather, you are controlling this current. Okay. So field controlled alternator, this alternator, that's why the name field controlled alternator. This rectifier is field controlled. That means that basically the field winding current of this alternator is achieved here, and that is actually having the control of field current of the generator. So field controlled alternator rectifier excitation system. Okay, so control of field current here is being achieved by controlling the field current of the exciter through this control rectifier. That's why this is the name. Okay. Alternate form uses a pilot exciter as source of exciter field power. Actually, there are many variations available. We have some typical configuration of the excitation system we are showing, because there may be many configurations. In one configuration, there may be again a separate generator, which is a pilot exciter. The role of the pilot exciter will be to deliver power or to control the field current of the main exciter. Okay, so these exciters, again, there will be separate exciter, which is the pilot exciter. Okay, the alternate form uses a pilot exciter as source of exciter field current. So this is the exciter. Its field current may be controlled by again a pilot exciter, separate exciter. Okay, these are the variations available. Okay. Then alternator supplied controlled rectifier excitation system. That was uncontrolled rectifier. This here immediately who is controlling the field current of the generator, it is done with the help of some uncontrolled rectifier. Now here we shall be using a controlled rectifier here. This rectifier is controlled using. This is another configuration, which is alternator supplied controlled rectifier excitation system. Again, this is the main generator, this is the field winding, this is the slip ring. Okay, because the alternator field winding is rotating. So this is the stationary diode, stationary rectifier, sorry, the control rectifier, not diode here, so stationary converter rather. Okay, and this is the slip ring. So you will be controlling the output voltage here will be available. So you will be controlling this rectifier, means you will be controlling the conduction of the that voltage, which will control the field current of the exciter. Again, there are two exciters. One is DC regulator, another is AC regulator. Again, they will be in parallel. Either DC regulator will be operating or AC regulator will be operating. Initially, AC regulator will not be available because it will take some time to generate the voltage here. So during that period, DC regulator, that means during starting, DC regulator will be in operation. Sometimes it may so happen that problems have generated in the AC regulator. Any component may fail. Okay, any component may fail. So if there is any failure in the AC regulator, then it has to be maintained. It has to go for maintenance purpose. Then who will be looking after the regulation of the voltage? Then the DC regulator. So DC regulator will be operating when AC regulator will not be available. When AC regulator will not be available, when you are starting the generator, then AC regulator will not be available. Again, when there is a fault in the AC regulator, then also it will not be available. So input to the AC regulator is as before. Inputs are as before. AC reference means what is the voltage record here. Then output from CTPT, that means that terminal voltage transducer and load compensator, and auxiliary inputs are those limiter circuit, protective circuit, uh, limiter circuit, protective circuit, and that power system stabilizer. Okay. Here, therefore, it is function of these regulators is to control the rectifier, stationary control rectifier system that will control the field current. That means you see the response of this configuration will be faster. Why? Because directly you can have a control on the field current here. Previously, you did not have a control on the field current here. You had to control the output voltage that has controlled the field current of the main generator. But here you are having a separate control. Not only that, you are controlling the generated voltage of the generator also, of this of exciter also. So exciter again is having a separate regulator. This is the exciter regulator, and this is the regulator of the field winding. Regulator of the field winding here. Okay. So exciter alternator is self-excited. Here this alternator is self-excited. The terminal voltage is measured. It is stepped down, and the exciter regulator is controlled here. Field current of this regulator is controlled. Okay. Excited and uses an independent static voltage regulator. Again, at static voltage regulator, the electronic regulator, basically that regulator that's named the static voltage regulator is used to maintain its output voltage. So separately this voltage is controlled and separately the field current is controlled. Okay. That means if this voltage will be controlled and the function of the diode, function of the rectifier here, basically it is not the diode, is rectifier here, control rectifier here is to control the conduction of this voltage, okay, such that the desired current will flow through the field winding. Okay. Small independent static voltage regulator to maintain its output voltage. Small response time. I have mentioned response time will be very small. It will be very fast. Why? As a thyristor directly controls the exciter output DC voltage. Okay, thyristor directly controls the exciter. That means this voltage is available here. Then what voltage will be applied to drive the field current of the generator? That is again separately controlled. Because of these two control, this separate control, this excitation system is much faster. Okay. Alright. So small response time as the thyristor directly controls the exciter output voltage. Alright. Then rotating rectifier type brushless excitation system. This is very popular. Rotating here brushless. You see that in the previous configurations. There were some limitations. What are the limitations? Here, the field winding is on the rotor of the generator. Okay, field winding is rotating and rectifier is stationary. So you have to take the help of slip rings. And since you are using the help of slip rings, there are chances of sparking here. This is the limitation. Okay. Again, see here, this configuration also you have to use the slip rings. The same problem. So this stationary rectifier system has the problem that they have to use slip rings. Now here it is, the rectifier is rotating. How it will be rotating? Because you cannot change the position of the field winding of the generator. Field winding of the generator, because it is a lower power circuit, has to be on the rotor. Okay, so field winding will be rotating. So therefore, you will be placing the rectifier now on the rotor shaft. So if the rectifier is placed on the rotor shaft, then obviously rectifier is rotating. That's why it is the rotating rectifier type, and also it is brushless. Why brushless? Because your rectifier is rotating. Directly, the rectifier is stationary with respect to field winding. Previously, rectifier is not stationary with respect to the field winding. Field winding was rotating, that's why you required a slip ring. Now, you need not use a slip ring because rectifier is rotating and, sorry, rectifier is rotating and field winding of the generator is also rotating, and they are actually placed on the same shaft. So there is no relative speed, so brush is not required. That's why the name is brushless extraction system. So brushless extraction system can avoid some of the problems, some of the maintenance problem. You can say why they can avoid this maintenance problem, because the slip ring is a source of problem, because there will be some commutation problem. Not, there will be some sparking rather, not commutation problem. There will be some sparking because of rotating. Current is flowing from a stationary body to a rotating body. There is contact, so contact pressure cannot be always kept fixed at the same value. So whenever there is a problem of there is rotation, there is creation of contact resistance, there is the presence of spark. Okay, so rectifier is mounted on generator shaft. These are the steps I should say. Rectifier mounted, so you see there, this is the armature of the generator, the TPT, and regulator. One thing you'll note here that we are not using any separate DC regulator here. The regulator is same regulator. Okay, taking from the output of the generator, these inputs and auxiliary inputs, already those power system stabilizer and all these things. And some manual control are also present. This is the means the absence of this DC regulator is replaced, okay, with the help of this manual control. So initially during the starting of the generator, obviously, where is the voltage? Where is the current? The generator is not delivering anything. Initially, generator has to build up. Generator has to build up the voltage. So then only you can measure it. Then only you can control it. Okay, but before that is available, you have to control the generator voltage, generated voltage by using the manual control. Okay, and this total part is rotating. What is there in the rotating part? It is the field winding of the generator. It is the control rectifier here. Okay, then it is the exciter. Exciter armature. It will be generating voltage, and you have the rectifier. Total rectifier here. It is control rectifier. It can apply control because it is not stationary. It can measure. Okay, it can take and decide how much will be the generated voltage and all these things. Okay, and here you have the field winding, which is using a permanent magnet. This is a permanent magnet generator. Okay, and basically the pilot exciter is here. Field of the pilot exciter is shown here. So you are controlling the through regulator. You are controlling the field current of the pilot exciter. So pilot exciter is a separate exciter that is responsible for the actually no sorry the field winding of the generator. It is the for the pilot exciter, and this field winding is for the for this generator. So you are controlling the field current of the main exciter, and pilot exciter basically is a permanent magnet generator. Okay, output of the pilot exciter is controlled by this regulator. This regulator then controls the field winding of this main exciter. Main exciter output is controlled, and the main generator field current is controlled. So rectifier mounted on generator shaft. Okay, since it is rotating rectifier, it is mounted the generator shaft. No slip ring and brushes. This is the advantage. You need not apply a slip ring and brushes because both are rotating on the same shaft, so they are stationary with respect to each other. DC output directly fed to the generator field. Okay, so whatever this output is obtained, it is fed to the generator field here. Permanent magnet field of the pilot exciter, this field winding rotates on the generator shaft. So on the same generator shaft, this here, it is the permanent magnet field winding. Okay. Now, voltage regulator controls the exciter, controls the AC exciter field. This voltage regulator, AC exciter field is this one, armature here, this is the field winding. So voltage regulator controls the field current of the main exciter. Okay, and this field current is controlled by the this exciter. So voltage regulator controls the AC exciter field, which in turn controls the main generator field. So this voltage is controlled, and then the generator voltage is controlled to control the field. Direct measurement of generator field current and voltage, uh, generator field current and voltage. That means this voltage, how much is the voltage here? Okay, that is not possible. In the other cases, you could measure it by using this distributor or that, because this was measurable. Now you cannot, because this is rotating, this part is rotating, you cannot, sorry, this part is rotating, you cannot measure it. So direct measurement of generator field current or voltage is not possible. You cannot measure how much is the voltage available here, you cannot measure how much the current is available here. So these are the features of this brushless excitation system. Advantage is that here you have no slip ring or brushes, so you have less maintenance is required here. Though one disadvantage is there is again one component. This is the pilot exciter, but obviously for some advantage you have to sacrifice some other place. So you can avoid the rotation in the between the field winding of the generator and the controller. Okay, field current controller. So that is avoided, but you require a separate pilot exciter. Okay, but by proper design, you can have low response time in this case also. Okay, then static excitation system, the last time. Previously we have mentioned regarding the DC excitation system, then the AC excitation system, now the static excitation system. In static excitation system, you have less number of components, and already I mentioned that as number of components are less, you are having greater and greater reliability, because low components, small number of components means small source of problems. Number of problems maybe are smaller here. Okay, what are there? Is the main generator, armature, field winding of the generator. Obviously, you require a slip ring here because field winding is rotating. So generator voltage will be stepped down through a transformer, which is the exciter transformer. Okay, there is no separate exciter. The same generator, because the generator is self-excited, the same generator output voltage is stepped down and rectified. Okay, how it is rectified? Who controls the rectification? By means of DC regulator and AC regulator. Again, this DC and AC regulator, as in all other cases, one of them, either of them will operate, not the both simultaneously. Okay, during starting DC regulator, during fault in AC system DC regulator, and when starting is complete and DC regulator, when you can have this voltage, then AC regulator will be taken. Okay, obviously when AC regulator is in fault, then DC regulator will function. Okay, so what are the features? Generator output voltage through step down transformer is rectified. Generated voltage, already I mentioned that basically in all system generated voltage is medium voltage level. Okay, 11 kV, 13 kV of this order voltage. So that voltage has to be stepped down for transmission purpose. But here you require a separate exciter transformer here, because you have to reduce the voltage, you have to step down the voltage. So generator output voltage through step down transformer is rectified. Sometimes output is taken from auxiliary winding of generator. Generator sometimes is having, you can actually step down maybe avoid. Sometimes you may take the output from an auxiliary winding. Generator may have a separate winding, because the generator is self-excited. So generator may have a separate winding where the reduced voltage will be generated and that voltage will be rectified. Very small inherent time constant. It is very, very fast. Why very fast? Because You need not control a separate exciter, separate generator. It is voltage generator is available. You can rectify and control this voltage directly. So number of steps are less. The control is very, very fast. Very small inherent time constant. The maximum output voltage depends on input AC voltage. This is a limitation. The maximum exciter output voltage depends on input AC voltage. What is the maximum voltage exciter? That what is the you can say whenever we have discussed regarding the requirement, then we have mentioned that generator must have a high ceiling voltage, and that voltage will depend upon the voltage available here. So maximum, because you are what you are doing, you are rectifying the voltage available, and that maximum voltage is available for to you only. Okay, so maximum exciter output voltage depends on input AC voltage. How much voltage is available here? That decides the how much voltage will be available to the exciter. Hmm. During fault, the exciter ceiling voltage is reduced. This is a very important limitation of this regulator. Okay, try to understand this. During fault, in fault may occur in power system, and actually, when we require the control from static expansion system, it has to they have to be most efficient when we have to control the transient stability or dynamic stability. During transient stability, it may so happen that the problem, the root cause of the problem is very near to the generator. Maybe there is a fault that has occurred very close to the generator. So, if the fault is very close to the generator, then what will happen? The terminal voltage will be reduced. But you are taking the that voltage for driving the field current. So available voltage will be reduced here. So during fault, the exciter ceiling voltage is reduced because of this basic feature. Available voltage will be reduced during a fault, and that voltage you are using for driving the field current. So this is a great limitation. Less expensive and easy maintenance. Less expensive because number of components are less. No separate exciter is required. No separate exciter generator is needed. So less expensive. At the same time, maintenance is easy because number of components are less. Maintenance is easy, more reliable obviously. In reliable in terms of component failure. Okay. Perform satisfactorily for generator connected to large power systems. When you are considering a large power system, then obviously the performance will be. That means in large power systems, since there are so many generators, you have less dependence on a single generator. So in that sense, you can say that performance satisfactory for generator connected to large power system, because for large power system many generators are available. If fault occur and transmission power system, then now the control may be taken over by other generators. So their performance will be satisfactory. But in case of a smaller power system, when you have more dependence on this generator, then if fault occurs near the generator, then this may be somewhat problem, because when the maximum service is required, then you are not getting the service. This is maybe the situation. Okay, self-excited. Obviously, terminal voltage is rectified and given as input to the field winding. Self-excited requires other source during starting for a few seconds. Since it is a self-excited, where from the current will come, you have to depend upon the residual magnetism. Okay, but if the residual magnetism is too low, so you have to give some extra support. What is this extra support? Initially, you have to depend upon some battery system maybe that will deliver the initial flash of current to the generator field. So initially, you require a separate source, maybe very very small time, because it will just start and disconnect it. That is required, but it requires other source. Basically, battery is used in this case during starting for a few seconds. So for a very small time, it is needed because it will be delivering that required initial current, and then voltage will be built up. It will start building up. Then the voltage will be utilized to build up the generator further. Okay, this process, that means initially giving a starting current to the field winding of the generator for a very small period, a few seconds. This is called field flashing. That means a flash of current is required for starting generator. That's why the name is free flashing. Okay, from station battery. In power station, you will have battery available for many purposes. For operation of the relays, it is required. For operation of other controllers, it is required. Similarly, for the functioning of the self-excited generator, for delivering driving current, initial current to the self-excited generator, that will just initiate the generation of voltage. Once a voltage is generated, you are getting that voltage to be rectified and fed to the field winding of the generator. So initially, in require separate support. Okay. Here also, regulator are two types. Initially, when the generator is started, okay, you will be controlling or depending upon DC regulator, because the generator has to build up. Then only you will be using this AC generator out. That's why two regulators are needed. Okay. So these are some features or some variations, some different types available in respect of the excitation system. What are the types available, how they function, what are their benefits. These things we have discussed. And you know that for the operation of power system, is PD control, first control of excitation system, is very essential. This is required for the control of reactive power. This is required for the control of stability, that means transient stability and dynamic stability. Not only that, it is required for the regulation of the terminal voltage. Terminal voltage has to be regulated. When the load changes, you have to control the terminal voltage. You have to change the field current, and hence you have to control the terminal voltage. Okay, so these are some descriptions, some issues related to the excitation system. I have discussed it today. Okay, so this more or less completes my content, whatever content I have to deliver. This finishes that, except one thing, except the numerical examples. I have not considered, I have not discussed on the frequency control. So that some problems, some numerical example, these are will be very instructive problems. There is some typically chosen problem. This problem will be discussed, numerical examples will be discussed in our next class. And I have actually mailed all the files, all the PPTs to you already. And last day, yesterday, I have mailed you uh, PPT on stability also. I shall be sending this PPT today to you. And in our next class, that is this Friday, I shall be discussing the numerical examples on frequency control. And if you feel that some more things are to be discussed, some of the issues, whatever I have discussed so far, some of the issues require rediscussion, then I shall do it. Or if you have some questions in your mind, you will be actually interacting with me, and we shall be discussing all these things. Okay. Now, if you are having any question today, you may ask me. Bolo. Any questions?
No, sir.
Okay. So let me then make roll call today, and then the next class. Okay, just 1 minute. I have to bring the just 1 minute. I have to see your name today. That is
Sir, you can stop the recording.
okay. I can now. This is the okay. Aditya Rai.
Yes, sir.
Then Alag Janri Murmu.
Yes, sir.
Amrita Datto.
Yes, sir.
Anirudh Anand. Anirudh Anand. Yes, you are responding, but somehow the sound is not reaching me. Arijit Pal.
Yes, sir.
Vikas Kumar Barnwal.
Present, sir.
Then Dipankar Singh.
Yes, sir.
Hasibur Rahman, Hasibur, Konishka Basak,
Present, sir.
Kaushik Maji, Ritam Khamaru,
Yes, sir.
Shreyas Khatri,
Yes, sir. Yes, sir.
Mohammad Sohail,
Yes, sir.
Showdeep Sen,
Yes, sir.
Shubhadeep Bera,
Yes, sir.
Mukesh Murmu.
Yes, sir.
Okay, Honorable Anand is present. He is writing. Okay. Shubhankar Mandal, Swapnil Kisku.
Sir.
Okay. Ujjal Haldar.
Yes, sir.
Okay. So